Yeah, thank you very much, Anket, for the kind introduction, and thanks a lot for inviting me. So it's a great pleasure for me to be here today, this morning, and give an overview of 3 projects that are ongoing in my team, the EcoVision Lab at the University of Zurich. And actually, the first 2 will be about environmental monitoring, and then the third will not, but I thought I would still sneak it in because it's so interesting. All right, so the first one, we look at snow depth estimation from satellite imagery. And then the second one, we look at a new line of research that we are building up in my team, which is about biodiversity and more specifically species distribution modeling. And I will show you this very first step that we are taking. And I hope I could convince you why this is a promising research direction for all of us. And then third, I will talk about the remote monitoring of armed conflicts project, which Olivier Dietrich is doing, who is also attending and here today. All right, so snow depth monitoring in Switzerland. So this project was accomplished and implemented by Rodrigo Cayedao, a postdoc, who is now at Sony working as a senior researcher. So why is that interesting, snow depth monitoring? Maybe you know this. So Switzerland is a very mountainous country, and a lot of the electricity comes from hydroelectric power plants. And maybe what you don't know is that in general, it's an energy scarce country. So overall, over the whole year, Switzerland has to import electric power from the neighboring countries. And now in the situation that natural gas is short in supply, there's a serious question: how do we better manage hydroelectric power plants? And a lot of the water that basically runs through the power plants is captured in the snow. Yeah? So in winter, there's a lot of snowfall, and there was a lot of rain now in summer too. So in the high alpine regions, there's also now a lot of snow. And we want to know how much snow is there to then predict big melt events and how much hydroelectric power can be produced when, at what time, where in Switzerland. So what we need for this is a high resolution, reliable snow depth prediction or snow water equivalent prediction. And in addition to that, we want to know how much can we trust the model. So we also want well-calibrated uncertainties together with that. So what we did, or what Rodrigo did, is that he developed a time series model. So that basically every 7 days predicts the snow depth at the 10-meter grid spacing all over Switzerland. And as input, we use Sentinel-1 synthetic aperture radar images to be a bit more independent from the cloud coverage, but it comes with disadvantages in the mountains. Sentinel-2, so optical multispectral images, and a digital elevation model. So what Rodrigo did is that he computes composite images. So in traditional remote sensing speak, we would say mosaics. And every 7 days, so once a week, he collects all the most actual and recent data from Sentinel-1 SAR images and from the Sentinel-2 images. And this means that each and every pixel can be taken at a slightly different day because we want to get rid of the cloud. So some of the pixels might actually be older than 7 days in the optical data. And then he designed a recurrent neural network with convolutional GRU cells, where he inputs basically this stack of mosaics plus the DEM and some derivatives, so the slope and so on, such that the RNN, the convolutional group, doesn't have to learn the slope. Of course, it could, right? But it's easier to put it in directly. And then the reference data comes from our partner in the project, from this startup company called ExoLabs. And ExoLabs has developed a method that uses an unsupervised approach for snow depth prediction and mapping based on spectral indices. So there's a lot of work out there that basically uses simple spectral indices from Sentinel-2 images or MODIS data and so on to then estimate the snow depth. And it's calibrated using point measurements on the ground. So all over Switzerland, there is basically testing facilities somewhere in the Alps, where they measure continuously at points the snow depth, but there's only probably 100 or 150 of these all over the country. And this is our reference data. Yeah? So this is the reference data that we use to train our RNN. And then to get the high frequency details in, what we also have is very highly accurate reference data around the area of Davos. So this is in Graubünden, in high alpine terrain, where we get UAV, so drone flights, multiple in a row over the whole winter season, that basically then subtract the digital surface models after structure from motion processing of the images of the drones. And this is basically what we use then for fine-tuning the RNN. So we have this unsupervised index-based reference data to compute for the whole country, and the RNN, and then we fine-tune on some very high-resolution drone data for the snow depth, but only in small parts. And what we also do is a bit the sort of nowadays almost classic thing that Nico already did for the canopy height estimation, that we use a negative log likelihood loss to get at least part of the uncertainties, which we then output together for each of every pixel together with the snow depth. So for each and every 10-meter grid cell, we have the snow depth, and we also have an uncertainty, so aleatoric in this case. And so this is such a result. So this is the snow depth on your left side, and everything very bright and orange is very high snow cover, and everything dark has almost no snow cover. And then on the right side, you see the variances, so the uncertainty here, and everything very light and bright blue is high uncertainties, and everything very low is not. So you see the higher the snow depth, the higher the uncertainty, basically. And here's a direct comparison. So on the left side, you see such a temporal composite, so such a mosaic from the Sentinel-2 multispectral image, how it looks like, which is fed an input to the RNN. And then in the center, you see the previous map, which acts as our reference data to train the model. Also, so not, of course, we separate train and test locations, of course, validation. So this is what the previous product, the unsupervised one, based on spectral indices from Exolex looked like. And on the right side, you see our new map. And you see that there, now we get a lot of high frequency details. And then we compute, of course, all the metrics, so all the details are in the paper. But we get a mean absolute error of around 60 centimeters. So which sounds pretty low in accuracy, not good, but it's already much better than state of the art, everything that we had before. But what is more important also for hydroelectric power plants, because they often might not even care about the mean absolute error so much, but they are interested about the bias. And a good indicator for bias is the mean error, and the mean error here is very low, so 6 centimeters all across the country. And some more examples, same thing. So always on the left side is the original Sentinel-2 mosaic image. In the center is what we had before. So based on unsupervised prediction calibrated with ground measurements. And always on the right side is the very high frequency outputs of our models that we now have every 7 days. You see that you can actually identify a lot of details, which now also feeds into ski touring apps, actually. So this is a product now. This is available in the app called Mountain now. There's other apps that use the same thing. So on the top left, you see an example scene, the famous city of Mürren, which is facing the Eiger North face. So it's a very beautiful village there. It's very expensive too, so I rarely go. But if you would want to go, and you want to plan your ski touring, and you would have the old products on the top right, so kilometer scale, not much to see. Also the previous one, unsupervised, there's not so much, but now if you use this new map that Exolabs has taken over in the product as a company and given to the Mountain Now app, you can actually see what path should I do when I do ski touring. But as I said, this is more like a cool touristy fun application. The real underlying motivation is hydroelectric power plant planning. All right. So this was the first. Yes. Yes, exactly. But of course not at the places where we test, right?
the accuracy that you're reporting around centimeters, the 60 centimeters, is compared to the ground measurements that you have yourself already?
No, no. So this is compared to the very high resolution ground measurements from the drone data for the holdout test data set. Yeah. Because otherwise it would not be not a reliable reference. Yeah. Yes, more questions for this first topic you can also ask at the end. Yes, please.
So if the mean error is the error of bias, mean error is 6 centimeters approximately. Like I'm just trying to figure this out. How because these 6 centimeters probably fall within the uncertainty of your input product, also the and images. So how can that be? I would need to read the I'm just confused a little bit. If the input probably has a higher uncertainty than this 6 centimeters.
So of course there's a connection, but you can actually not deduce this directly because the uncertainty basically doesn't tell you whether it's overestimating or underestimating, right? So, but the bias does tell you. So a high uncertainty does not necessarily lead to a high bias. Because like over the whole thing, overestimation, underestimation averages out. Yeah. So for ski touring, that's still not good because you want to know at each and every point how much snow is there less or more. But for hydroelectric power planning, it doesn't matter so much because the snow melt events, you look at them on larger scales. Yeah. So for those, the uncertainties, they are important, but more over larger areas if they aggregate them. So the bias over larger areas needs to be close to zero. So you don't get much more water than you expect or much worse, much less. Yeah. Okay. Yeah,
so what is the trade-off? So not exactly this map, right? So
no, yes, exactly. So we basically have geographic regions for training, for validation, for testing.
But I mean, so this is the interpolation of some data from ExoLab or
no? No, so the bottom left map, that's the ExoLab map, right? But we didn't use it for training for exactly the scene where we predicted on the top right? So we geographically make sure that train validation tests don't overlap.
So how come your map has a higher resolution than the ExoLab?
So the ExoLab's map, because it's based on spectral indices, and they also use Sentinel-2 images, but they get just a much smoother result. Because there's no supervised learning, nothing. It's the spectral response basically apparently doesn't change so quickly, and there's no learning involved. So it's just a much smoother map. The resolution, that's the thing, right? The grid spacing is similar to ours. I think it's also 10 meters or 20 meters or something, but the result is much smoother. So that's it. You have to differentiate between the grid spacing, right, and the actual physical resolution. The grid spacing is probably similar to ours. I would have to check the paper again. Okay, I think I'll just move on and you can ask me a lot of questions afterwards, otherwise I run completely over time. So, so let's look at the second topic, species distribution models for satellite imagery. And this is a collaboration ongoing with WSL in Bermensdorf. So that's part of the ETH framework. And this is done by a PhD project by Johannes Dollinger, a PhD student in my team. And the idea of species distribution models is that you want to know what species live at what place at what time on Earth. And we all know that this is a big issue, that we are losing biodiversity, we are losing a lot of precious species. So the first thing is we need to measure what we have to track the decline and then possibly to work against it. And until now, how it's done is that basically each species is modeled individually. So each bird species is modeled individually, it's plant species and so on. And we think that modern machine learning, deep learning, provide a really promising tool to model basically distributions of species jointly and get very high dimensional evidence together to better model species. And we have the first groups progressive groups in biodiversity on board, but there's of course still a lot of resistance. We have seen this with Nico's project in the past for canopy height and so, but I think we have a good case for us. So, and what are the inputs? So the climate data, we have climate data decades back that we can use, reprocess pretty accurate climate data. We have digital elevation models and the derivatives. And what we also use is satellite data again, so Sentinel-2, multispectral optical data in this case. And we also combine it with crowdsourced data in the field. So probably you all know this, there's a lot of work here also going on in Copenhagen on working with the GBIF data set or iNaturalist data in Switzerland. In France, there's PlanNet. In Switzerland, there's the same thing. The app is called the Floor app. And the idea is now when we have basically all this input data and the crowdsourced data, how can we basically then predict a probability map or uncertainty map for predict each and every species that we want to predict for. And we do this using a neural network. And this is the approach called SUD-SINNER because it's based on the now seminal famous SINNER paper from Elijah Cole and led by Ocean McKay. And so the setting is this, that you have, this is a specific oak tree. I forgot the Latin name, not good in Latin. So, and this is basically mostly a growth in the Mediterranean. Yeah? And all the green dots are presence data. So this is where a user has used an app. So let's say iNaturalist or PlanNet probably in France, taken a photo of this oak tree and said it's growing here with a GPS coordinate. And what we want to do now, using this as input, we want to basically predict the probability map, where else is this tree growing. And we don't want to only do this for the specific oak tree, but for thousands of species. So this is then such an output, how it looks like. So high probabilities are yellowish and bright, and low probabilities are dark blue. So, and this is based on this original SINNER paper by Cole and collaborators led by Ocean, that many of you might also know, University of Edinburgh. And it's based on the data set assembled by GeoLifeClef team. So a big shout out to them, fantastic data set that got us started. And they sort of, one of the important contributions of the Cole paper is that they handle these particular situations with the presence and absence data. So if you want to train a classical model, you need to know your foreground labels. So you know, in our case, where is the species occurring and all the places where it's occurring. And you need to have background labels. So all the places where it's definitely not occurring. But we don't have this in our data. Yeah, we only have presence data and it's not complete. So we basically have presence data crowdsourced, so we know where the oak tree is growing in some of its places, but not all of its places. But we don't know anything about the background, because in other places, when other species are sampled, maybe I know some birch, some beech tree or something, we don't know if it's only the beech tree or if there's also an oak tree. Maybe it has not been photographed and not sampled, but still growing there. And what they basically say, well, we take for the foreground labels, so for our oak tree, we take this target at the data location where it has been crowdsourced, but for the background, we randomly sample across the scene. And this is then the setup that they chose. So it's a very simple network, nothing fancy at all. It's just a basically cascade of ResNet blocks. And you basically input the location. There's no satellite images. There's inputs only the location. And at the end, you basically predict what is growing where. It's basically a smart way to interpolate between the locations. And we will abbreviate all this now to SINNER, location in, SINNER, then prediction. And what Johannes did is basically that he now adds satellite data to this, and he also adds climate data, and he chose a very simple embedding here, just a CNN. And this is, of course, now also the place. We are in the self-supervised learning workshop here. I don't show much about it, but this is exactly a place, of course, where a good embedding, a good foundational model about basically Sentinel-2 images for areas that are interesting for biodiversity would help. And what he then tried, Johannes, is that he had 3 different strategies. So he had an early fusion thing. So he jointly inputs the location data, environmental data, so climate data, and the satellite data. The second one was late fusion, so he runs Sinner as usual, but then he also encodes the satellite data. He does the late fusion and basically adds both encodings, does a prediction, and then he also did the middle fusion. So this comes from I think the EfficientNet paper, if I'm not mistaken. So basically that you gradually feed evidence from the satellite data in each and every ResNet block and add it gradually such that it jointly learns to basically extract evidence from the satellite data and the location and the environmental data. And then the testing was done on much better data. So actually present absence surveys. So this is in the GeoLifeClap data set. So this is where people actually went and for specific sites in France and in the UK, where they really looked, okay, they sampled all the species that are occurring at certain places and also all the species that are absent at those places. So this is really basically the best available data that we can have, but in much smaller portions, and it's only for testing. So and this is then some results. So this is the original SIN, and those are the metrics that are used in biodiversity, species distribution modeling, and I won't go into detail. The definition of those are in the paper and also in the original SINA paper. So, and what we get if we add satellite data in early fusion, we get basically almost doubling of this so-called micro F1. So this is the most important measure, basically an F1 score for the top predicted species. We almost double that. So we see there's a lot of evidence in the satellite data, and we increase the parameters size only marginally by 0.3 million. Then if we do late fusion, again with the satellite data, we improve a little bit on top. And I also give you the standard deviation, so the plus minus. Of course, we did 4 or 5 runs always. But you see that for late fusion, we already add a lot of additional parameters, 2.9 million. And then the one that we choose for the rest of the experiments, the middle fusion, most sophisticated one with the most of the parameters added, where we also got a bit less improvement of micro F1, but what was more important to us, we got a lower standard deviation on the prediction. So all the ensemble members are more trustworthy. We got a lower spread of the results. So and this is then a comparison. So if you only use the location input for the SINner on the left, and you see, and then if you use the middle fusion SAT-SINner on the right, and you see, again, you get a much more fine-grained results. And because we have the satellite images as input, so we have actual evidence from the ground, you see much more fine-grained details. And I will just highlight the region around Paris on the top in the red circle. And this is, of course, like always a bit the sampling bias of crowdsourced apps, that if there's a lot of people living, a lot of data gets sampled. And the SINA model, what it does for this is again for the oak tree that I showed you earlier, this example, the green points, is it just interpolates. Yeah, if you look on the left image between Paris and Normandy, Brittany, you see there's a high probability, there's a lot of oak trees between Paris and this place. But our model on the right side does this better because it understands that these oak trees are actually not just growing anywhere and cannot just interpolate the location, but it looks at the actual spectral evidence of the satellite images for this. And what you also see in the bottom red oval circle, that there seems to be a lot of probability for this oak tree growing somewhere between, let's say, the center of France going down to Provence and Côte d'Azur. Yeah. And this is interesting because if you look on the map, this is the Loire River Valley. Yeah? So there's a lot of water there. And this is actually, when you look it up in textbooks, where this oak tree species actually also grows. So it sort of implicitly picks up a lot of evidence that otherwise would be hidden. This is the strength, well, of satellite data, but especially of deep nets. Okay, so I won't bore you with too many numbers. The message is just that if you have all of these encodings, so the location, the climate data, the digital elevation model, the satellite data, you get a significant improvement in basically all of the scores. And this is, of course, just some incremental contribution on top of SINA. So we didn't change the main model, the main loss, nothing, but already small steps to help. And we do think this is a very promising direction for all of us. There's a lot of very cool technical problems that we need to deal with. So long tail distributions, uncertainty quantification, this presence absence problems. And again, it's a problem that has societal relevance. So this is something I think should encourage all of us to look into this. And of course, we can use Nico's maps as well as input there. That's fantastic. Okay, so last topic is what Olivier is working on. And this is a project that is funded by the so-called Humanitarian Action Challenge grants. And this is a grant basically funded by the federal government of Switzerland because NGOs like the International Committee of the Red Cross, the ICRC, they basically have no capacity and no funding to innovate in the technical domain, because they need all their resources to help people on the ground, to map manually and so on, that basically there needs to be external advisors and support to help them improve the whole processing workflow. And the idea of this project that was initiated by Valerie Sticher, a political sciences colleague here, is that we develop a tool that does global screening for destruction caused by conflict. So we basically, what the Red Cross is doing at the moment, they call people on the ground, or people call them, say, look, something is happening here, please help us. Or what they can also do is that they buy high-resolution satellite images from Maxa or Planet, and then they manually annotate. But this doesn't scale. It's very expensive for them. So our idea was to come up with a screening tool that says, look, possibly something is happening here, again, with well-calibrated probabilities and hopefully not too many false alarms. Now you can call people on the ground, or you buy a high-resolution satellite image. And this is especially important for conflicts that are not so much in the media. So I will show you examples for Ukraine now, because we have a lot of data there. But this is not the actual target of the project. The target is, for example, Sudan, Mali, Myanmar. So conflict zones where there is no people on the ground, no one who can actually call, who has cell phone reception, who can cry for help. And we started off, when I wrote the proposal, I thought Sentinel-2 data is excellent. So this is a comparison now for this, you might remember this case for this theater, I think in Mariupol at the time, and the high resolution on the left, when there's written children in front of it. But the Russian army was merciless and still bombarded it, the absolute catastrophe. Then in the center, you see the Sentinel-2 image. You see that the resolution goes down a lot. And on the right side, now you see the Sentinel-1 synthetic aperture radar image. And when I wrote the proposal, I thought, well, optical data is perfect. And we ran into a lot of trouble. It didn't work. And we tried with Sentinel-1 data, where as humans, we can see even less. But it proves to be a very, very rich data source if you approach it with machine learning. So what Olivier is doing is that all over Ukraine, he is basically looking for data from the United Nations that was manually labeled in different levels of destruction. So this section of the United Nations is called UNOSAT. They're based in New York City and in Geneva. And they manually label destructed buildings at different levels. And then he uses Sentinel-1, synthetic aperture radar time series. And he basically then looks over time and trains a machine learning model and outputs the destruction probability. So this is a whole workflow. So you basically stack the Sentinel-1 SAR images, and you have temporal T0. So this on the bottom left in green, it's basically before the war started, before February 2022. This is all background. We know there's no bombardment, at least outside of Donbass and Crimea. And then you do feature extraction, and you use that, and you input this. So this is all running on the Google Earth engine at the moment. You will input this to a random forest, and then the random forest classifier outputs a destruction probability. And then we don't stop there, but we overlay it with this building layer from Overture, Maps, Foundations, Open Map data. And we try to then condense it, bring it down to each and every building footprint. Of course, that's not perfect. So there are gaps in the data still, but it's the best that we have at the moment. So this is this intermediate result without the building footprint layer. So this is, you might all remember, this is Azovstal, huge factory at the coast of the Black Sea, Mariupol, which was heavily bombarded like a year or a bit more ago. And everything reddish is high destruction probability, and everything that is not so much has a lower probability. This is now overlaid to one of the Sentinel-1 SAR images, but keep in mind, we take a whole time series. And this is now how the workflow goes for three different scenes for A, B, and C that you see. So you overlay, basically, you have where the red dots are, we have some UNOSAT labels, so of our train and test regime. Then in the middle, you always see the destruction probability, that is the output of the random forest classifier on the Google Earth engine. And at the bottom of always these three images on the right side, on the bottom right, you see when it's basically then clipped to the building footprint from over maps. And the damage probability is again encoded from low, so bright, yellowish, to very high, very red. And then what Olivier did is that you can also basically have a sliding window over time. So you keep your background training intact, always before the war started, before 2022. And then, but for the foreground label, you gradually move over time. So you aggregate over the month. And this is now, you can basically follow the destruction, especially in the Donbas regions in the east of Ukraine. It gets more and more red, more and more gets destroyed. So this is the percentage of buildings damaged per administrative district. And keep in mind always that this is only a screening. So we have false alarms, of course. It's not perfect, but we believe it's a promising start. So yes, and then Olivier and postdoc Torben did the next step and basically turned this into an open source tool, this which can also be used by anyone now, but particularly by the ICRC. And there's two versions of this. So one is basically displaying the results that we got. And another one is that you can now also basically extract the damage for your area of interest inside Ukraine on demand. And it computes super quickly, but downloading the results is still a bit slow. So you have to invest 2 to 5 minutes to compute. And all right, so this brings me to my end. So there's some QR code here, but you find it online, or you ask Olivier, who has the links for you, to play with it and give us feedback, what you like and what you don't like. So in the end, what probably my main message is that Earth observation and deep learning are very, very important. Don't underestimate the potential of this. We all think it's normal, we've done it for years. Well, yes, we do, but many other people don't know. Many other people don't work with map data. They don't work with spatially explicit data. And I think it's absolutely essential for many, many applications to get global, consistent, actionable insights for fact-based decision-making. So this is super important. Don't underestimate this. And then what we have always done, and it's a tedious work, takes many years, but I can only encourage you, and I think this is a great place who does this, is that you should collaborate across disciplines to benefit society and the planet. It might take much more time. I remember from the work with Nico, we were sometimes very annoyed by the slow progress on our partner side, by the communication but in the end, this pays back. And it's amazing what you can achieve if you take the time, you communicate with your neighboring disciplines. And I think we as a community here, we are perfectly positioned to do this, to lead such efforts. With this, I thank you.